November 2020, paper 4, variant 1. Question 1. Figure 1.1 shows an ice hockey player moving on ice. He is preparing to hit a solid disc called the puck. Okay. Disc has a mass of 0.16 kilograms and is moving horizontally across the surface at a speed of 15 meters per second. Can I find the magnitude of the momentum? Yes, momentum equals P equals mv, which is 0.16 times 15, which gives you a final answer of 2.4. Do not forget the unit, kilogram dot meters per second. This is the momentum. The hockey player, okay. Okay, I guess this question is cancelled. Yes, this question is cancelled. It has been removed from your syllabus. You're not required to draw any. Yeah, you're not required to draw these diagrams. Okay, these force diagrams with an angle other than 90 degrees. You're not required to solve any questions with angles other than 90 degrees. So this angle is 45 degrees. You are not required to solve it. Okay, it has been removed from your syllabus. Question 2. A vertical tube contains liquid. A metal ball is held at rest by a thread. The diameter of the tube is much greater than the ball. Okay, describe what happens to the velocity of the ball in the short period of time as it accelerates downwards uniformly. Okay, as it accelerates down uniformly, what happens? We need to say that the speed, what happens to the speed? The speed increases. Speed increases. And as it accelerates uniformly, it increases at a constant rate. So the speed, okay, increases at a constant rate. Increases at a constant rate. Why? Because he's asking about that short period of time in which it accelerates uniformly. The ball then reaches the terminal velocity. Describe and explain the motion of the ball from when it is released until it reaches the terminal velocity. When it's released until it reaches the terminal velocity. This is quite easy. Okay, it's not that difficult to state what happens to the speed of the ball, what happens to the forces acting on the ball, what happens to the acceleration, all of these things. But first of all, initially it was moving down with a constant acceleration. Initially, it was moving down with a constant acceleration, and that's what we said in A. In B, we need to say, as the speed increases, what happens to the forces acting on the ball? Okay, as the speed increases, you need to say that the resistance, okay, it's falling in water, I guess, okay, or in some liquid. So as it's falling through this liquid, the resistance due to this liquid, or you can say the drag due to this liquid, air resistance in air, in water we can call it water resistance, in any liquid we can just call it drag. So the resistance due to this liquid, okay, resistance due to the liquid increases. The resistance due to the liquid increases. As the resistance increases, what happens to the resultant force? You need to say that the resultant force, okay, the resultant force decreases. Why? Because the as the resistant forces increases, therefore the forward force, which is the weight, or the downward force, which is the weight, is constant, and the resultant force decreases, thus resulting in a decrease in the acceleration. Therefore, the acceleration decreases. When the acceleration decreases, it finally reaches the terminal velocity. Okay, it finally reaches terminal velocity when, okay, when the acceleration equals zero, or when the resultant force is also equal to zero, at which the weight, the downward force, is equal to the drag or the upward force of the water. Okay. The metal ball has a mass of 2.1 grams. It falls a distance of zero point 0.8 meters between being released and touching the bottom of the tube. Distance, mass, can I find the gravitational potential energy? Yes, definitely I can find the gravitational potential energy. mg H, mass is 2.1 grams. You need to convert it to kilograms by dividing by 1000. So the mass is 0.0021 times G, which is 9.8. I know in the marking scheme it is 10, okay, times 9.8 times 0 0.8 meters. We don't need to convert it, okay. The final answer would be around 0.017 joules. This is the gravitational potential energy transferred as it falls down. When the ball reaches the bottom of the tube, it has a speed of 1.2 meters per second. Calculate the kinetic energy of the ball at the bottom of the tube. What is the kinetic energy? How can I find the kinetic energy? Half mv squared. Half mv squared. So basically half times 0.0021 times the velocity 1.2 squared. That's it. Okay. Kinetic energy would be around, it's a very small number, 0.0015. Okay. 0015 joules. There's a slight difference between the gravitational potential energy and the kinetic energy. Explain why the value calculated in CI is different than CII. Okay, why is it different? Why is there a slight difference? Because some of this energy is lost, okay, due to friction. Okay, it's lost due to friction, okay, or resistance, okay, friction, or you can say resistance or whatever. You have molecules surrounding it, so these molecules try to decrease the speed somehow. Okay, thermal energy is lost, whatever, to the environment. Okay, question 3 has been cancelled. Manometers, you're no longer required to solve manometers. Okay, at least part A. Part B, the area of the piston, you have the area, calculate the resultant force on the piston. You do not have the pressure, okay, so you won't be able to solve this question, okay, because you need the pressure from the previous question. You need the pressure from the previous question. So anyway, you don't have the pressure. So okay, we can just cancel out this whole question. Okay, but you can, so yeah, if we had the pressure, we would have said that force equals pressure times area, and if you needed to find the work done would have been force, the force that you found, okay, times the distance moved, But anyway, um, yeah, moving on. A large test tube contains a liquid at room temperature. An electric heater is immersed into the liquid and switched on. Thermal energy is supplied. Describe in terms of molecules, yeah, in terms of molecules and their motion, how liquid differs from gas. This is easy. Motion of the molecules, the distances, okay, between the molecules. How does the liquid differ from the gas? Definitely, the molecules are much closer in liquid. Liquid, we can say that the molecules are closer. We can say that they're touching. They are touching. We can say that the distances are very small. Distances are very small. Okay. Hmm. Very small. You can also say that they, what about the motion? The motion of the gases are fast and random in all directions, but in liquids, they slide over each other. They slide over each other in liquids. Describe what happens to molecules of the gas as the temperature begins to increase. What happens to the molecules of the gas? They gain kinetic energy. Okay? They gain kinetic energy. And as they gain kinetic energy, they move faster and further apart. Okay? So they gain kinetic energy, move faster, okay, and further apart. Gas molecules. Explain in terms of molecules why a supply of thermal energy is needed to change the liquid into a gas. You need to change a liquid into a gas. In terms of molecules, why do you need to supply energy? Because the molecules, initially there's a force, intermolecular forces between the molecules. You need to overcome these forces. How can you overcome these forces? By supplying energy. Okay, you need energy to overcome these forces. Okay, to overcome the forces. Hmm. The density of the liquid in the test tube is 0.86 grams per centimeters cubed. The volume of the liquid in test tube is 50 centimeters cubed. The liquid reaches a boiling point. It now absorbs 18,000 joules of thermal energy. You need to find the specific latent heat, which is cancelled. So III has been cancelled, has been removed from the syllabus. You're very lucky in this test, honestly. Yeah, question 5. A metal container is used to cook food. The metal container has thick walls, okay? The metal container has some thick walls. Explain how the rest of thermal energy is conducted through the metal. He talked about the neighboring molecules. He talked about the conduction, lattice vibration. So he talks about the lattice vibration. How about the remaining energy? How do you transfer the energy in the metals? Through the free moving electrons. Free moving electrons. Free moving electrons. If you want to say delocalized electrons, again, it's okay. Free moving electrons, what do? They move freely between, which is quite obvious, between the molecules, okay, and they transfer energy from the hot end, okay, transferring energy, okay, transfer energy from the hot end to the colder end, to the cold end by hitting the molecules or by colliding with the molecules. Okay, by hitting the molecules as they transfer between them. Okay, as they travel between them. Okay. Hmm. The outside surface of the container is brightly polished and shiny. Explain how this reduces the power that needs to be supplied to the to keep the oil at the correct temperature. Shiny, bright, white and shiny, whatever. How does this reduce the power needed? White and shiny surfaces are what? They are. Are they good or bad? Hmm. They're poor emitters. They're bad emitters. They're the worst emitters. Why did I say emitters? Why didn't I say absorbers? Because I want to keep the heat inside this container. Okay, you want to keep the supply of water. You want to keep it hot. Okay, so in this question, you have to say that the emitters, that the shiny surfaces, the white shiny surfaces, are the worst emitters of infrared radiation. Of infrared radiation. Okay, worst emitters of infrared radiation. So you can say that less energy is lost. Okay, less energy is lost. The metal container is spherical. Okay, the spherical container has a smaller surface area, than the long, thin container of the same volume. The spherical container has a smaller surface area. Explain the advantage of using a spherical container. The sphere, when you decrease the surface area, what happens to the amount of radiation given off? the amount of radiation decreases. Amount of radiation is directly proportional to the surface area. It's directly proportional to the heat or to the temperature. So as you decrease the surface area, what happens to the amount of radiation given off? It decreases. So you can say that less energy, okay, less energy is emitted, okay. Less energy is given off. Less energy is lost to the environment. Okay, less energy is lost to the environment. Okay, why? Because you're decreasing the surface area. Conduction, no, it doesn't have to do with conduction. And this question doesn't have to do with conduction. It has to do with the radiation. Okay, whether it's a good conductor or a poor conductor, the surface area does affect the amount of radiation. Okay, whether it is a good conduction or a poor conductor, surface area will definitely affect the amount of radiation. Hmm. Okay, question 6. You have the boundary, and then he's asking this wave which has passed from one medium to another medium. Explain why the direction of the wave fronts change. Direction of the wave fronts changes in the way shown in 6.1, in figure 6.1. Why do the waves change their directions? This is a question that has been repeated over and over and over. The speed changes. Okay, why do they change their direction? Because the speed changes. Why does the speed change? Because it's moving from one medium to another. It's moving from one medium to another, more dense to less dense, or less dense to more dense. So it's changing the medium, and therefore the speed changes. When the speed changes, mm, so why does it, I can change my speed and still move in the same direction. I can change my speed and still move in the same direction. The thing is, not all of the wave, or not all of this wave hits the boundary at the same time. Okay, only part of this wave hits the boundary before the remaining part of this wave. Okay, so for example, let's look at this compression. Okay, so this part has reached the boundary before the remaining part of the wave. Again, this part has reached the boundary before the remaining part of the wave. So only this part of the wave will start to slow down first, or will start to change its speed first. That's the point. That's the thing you need to think about. When it changes the speed, okay, well, it changes the speed. So what? Because only part of the wave reaches the boundary first. So as the speed changes, as the speed changes, okay, only part, okay, as the speed changes, only part of the wave front reaches the, or yeah, you can say crosses, okay, slows down first, okay, reaches, yeah, only part of the wavefront reaches the boundary first and starts, yeah, and starts to slow down, okay, and starts to slow down. When it starts to slow down, okay, as it moves from one end to the other end, okay, before the remaining part of the wave. When the remaining part of the wave reaches the boundary, then it will start to slow down as well. Okay, that's why it starts to change the direction. Okay, that's why it starts to change its direction. Okay. Hmm. The speed of the wave in the left hand part of the tank is 0.39 meters per second. Using this information, okay, use information from figure 6.1 to determine the frequency of the wave. Can I find the frequency of the wave? Yes, I have an equation. Speed equals wavelength times frequency, and therefore the frequency would be equal to speed over wavelength. The speed is 0.39. What is the wavelength on the left part? The wavelength 2.6. So is this the wavelength? Is this the wavelength? No, this is not the wavelength. The wavelength is the distance from a crest to the crest, or trough to trough, or rarefaction to rarefaction, or compression to compression. So this is only half the wavelength. 2.6 is only half the wavelength. So the actual wavelength is what is 5.2 centimeters. 5.2 centimeters. And then you need to actually convert 5.2 centimeters to meters. 5.2 centimeters to meters divided by 100, which is 0.052 meters. This is the wavelength. 0.052. 0.052. So the frequency would be around 7.5 hertz. Okay, this is the frequency. Again, 2.6 is not the wavelength. 2.6 is only half the wavelength. Okay, half the wavelength. Hmm. Moving on. Determine the speed of the wave in the right-hand side of the tank. The speed of the wave in the right-hand side of the tank. What is the speed of the wave in the right-hand side of the tank? Well, the speed should be, should it increase or decrease? Well, that's the question. Should it increase or decrease? If we check out the, yes, it should decrease. Thank you. Yes, it definitely should decrease. How did we know that it should decrease? Because if we look at the wave length, okay, if you look at the wavelength, what has happened to the wavelength? The wavelength has decreased. The wavelength has decreased. So when you decrease the wavelength, this means that the speed decreases. That the speed decreases. How can we find the speed? Again, how can we find the speed? We can use an equation. We can use the equation refractive index. We can use the equation of the refractive index. This is not light. Would it be the same? Yes, it would be the same. Okay, we would use the same equation. How can we use this equation? This is the, on the left hand side, it's the fast region. So technically you can say it's air. I know it's not air, okay, but it's the fast region. So if we compare the light is it's moving the fastest in air and then the slowest in a medium. So we can consider this part to be the air and this part to be the medium if we're talking about light. What is the equation, the refractive index that we use in light? Okay, speed, refractive index equals speed of light in air over speed of light in the medium. And we need the question, we need the speed of light in the medium. We don't have the refractive index, and we do not have the speed of the light, the speed of this wave in the medium. Is there another equation? Yes, there is another equation. N equals sine theta A over sine theta M. Sine theta A over sine theta M. So basically you can say sine theta A, the angle, over sine theta M. So for this equation, we can just cross multiply. We have the speed 0.39 over the speed in the medium. We don't know the speed in the medium over sine 45. Okay, over sine 30, 30, 33. Okay, over sine 33. Cross multiply sine 33. يلا. 0.39 times sine 33 over sine 45 would give you a final answer of 0.3 meters per second. 0.3 meters per second. Again, what did I do? I just cross multiplied. Can I find the refractive index and then use the refractive index to find the speed? Yes, you can do that. You can do this, that. Okay. Okay, so the final speed in the medium would be 0.3. How do I know that this is the correct answer? Because the speed is less than the initial speed. The initial speed was 0.39. 0.3 is less than 0.39, so we are on the right track. Okay, we are on the right track. Okay, well, question 7. A permanent magnet is made from only one material underline the material from which it is possible to make a permanent magnet. Definitely, we use steel for the permanent magnet. We use steel for the permanent magnet. Okay, an electron. Um, okay, an electron is moving through a magnetic field. Okay, how can we determine the direction of this electron? Okay, using the Fleming's right-hand rule. Describe what is meant by the direction of magnetic field first. Okay, um, what is the direction of the magnetic field? Again, we had the definition. We needed to memorize this definition. The direction of the magnetic field. It was the direction of the force. Okay, if you remember, if we had a compass, we put a compass in this magnetic field, and we looked how does this compass, direction of this compass will point to the right. Why will it point to the right? Because it's the direction of the force on the north pole, on the north pole of this compass. So it's the direction, okay, of the force on north pole of a small magnet or of another magnet, okay, of another magnet, okay. Let's write down a small magnet in the field, in this field. Direction of the compass, direction of the north pole of this, the force acting on this north pole inside this field. Okay. Hmm. Describe and explain what happens to a beam of electrons in the magnetic field between the poles of the magnet. Huh. Beam of electrons. Will they deflect? Yes, they will deflect. In which direction? Huh. Into the page, out of the page, to the left, to the right. Yes, into the page. Thank you. It will deflect into the page. How? Using Fleming's right-hand rule. Fleming's right-hand rule, in which the index finger is the direction from the north pole to the south pole. The middle finger, second finger, middle finger is the direction of the electron source, which is directed downwards. So the index finger is pointing to the right, the electron source is pointing downwards. Therefore, the thumb, which is the force acting on this electron source, the force is acting into the page. The force is acting into the page. That's it. Using Fleming's left hand or right hand rule if you want to. تاني يبقى electrons deflect. Electrons deflect into the page. Into the page. Why? Using Fleming's right hand rule. Okay. This is the force acting on an electron inside a magnetic field. Force acting on an electron inside a magnetic field. Okay, a beam consists of alpha particles, beta particles, and gamma rays. Explain how a uniform magnetic field may be used to separate the alpha particles, the beta particles, and the gamma rays. Uniform magnetic field. How would this separate them? How would it separate them? Because the alpha particles and the beta particles will both be deflected into separate directions. The gamma particles will move through the magnetic field undeflected. They will move through the magnetic field undeflected. So we can say that the gamma rays, okay, do not deflect. They're unaffected. Why? Because they have no charge, as they're moving at the speed of light, so they don't care about anything around them. Alpha particles and beta particles deflect in opposite directions. Alpha particles, okay, alpha particles and beta particles deflect in opposite directions. Okay, they deflect in opposite directions. That's it. That's all you need to say for this question. Hmm. Yeah. Explain what is meant by electromotive force. And again, electromotive force, it has an old definition and it has a newer definition. Okay, electromotive force has an old definition and it has a newer definition. Should I write down the old definition or should I write down the newer definition? Please write down the newer definition. Why? Because you need to memorize the definitions. Okay, we need to memorize these definitions. What is the electromotive force? We said it before. The electromotive force is the work done by a source. Work done by a source in moving this charge around a complete circuit. Okay, in moving a charge, okay, around a complete circuit, around a complete circuit. Electric work done on, okay, by the source on the charge, because the source supplies the charge with this energy. Electromotive force is the amount of energy per unit charge. Amount of energy per unit charge. So basically, you want to find the work done by the source on this charge. Okay, by the source on this charge. Hmm. In B, calculate the current in the heating element R1. The heater is powered by a main supply 240 volts. You have a motor, you have heater R1, you have heater R2. Switches S1 and S2, S1 and S2 are closed. Heating element R1 gets hot. The resistance of R1 is 30 ohms. Can I find the current? Yes, I can find the current. Current equals V over R. V over R. What is the voltage? يلا. Hmm. 240 volts. What is the resistance? 30 volts, so 30 ohms, so the current is 8 amperes. 8 amperes. Next question, can I find the power? Yes, I can find the power. Power equals IV or VI. يلا. IV, which is 8 times 240. 8 times 240, which is around 1900 watts. صح. The resistance of heating element R2 is 60 ohms. 60 ohms. R1 was 30 ohms, R2 was 60 ohms, switches S1 and 2, S1, 2, and 3 are closed. State and explain how the current in R2 compares to the current in R1. Well, this is easy. When you increase the resistance, what happens to the current? When you increase the resistance, the current decreases. Current A? Decreases. So the current is less, or actually, to be more accurate, it's half the value. So instead of being 8, it is 4 amperes. Okay? As resistance is increased, you can say double. Okay? The current is halved. Current is decreased, or to be more accurate, it is halved. Instead of 8 amperes, it is only 4 amperes. They are inversely proportional. Inversely proportional. All good? The current in the motor is zero point 0.1 amperes. The cable from the electrical heater okay, is safe when the current is less than 20 amperes. Suggest and explain a suitable fuse rating for this circuit. Suitable fuse rating for this circuit would be how much? The main question is, what is the total current in this circuit? Total current in the circuit would be, he said the motor has a current of zero point 0.1 amperes. Okay, so هنا zero point 0.1 amperes. R1 has a current of 8 amperes, and R2 we just said that the current would be 4 amperes. So the total current in the circuit is what? 12.1. So you can say zero point 0.1 plus 8 plus 4 is 12.1 amperes. It would be safe to use a fuse of, let's say, 14 amperes, 15 amperes. Anything greater than 12.1 and less than 20. Okay, so it would be suitable to use, okay, this is the total current, okay, this is the total current. Okay, fuse, if you say fuse 14 amperes. Okay, 15, okay, 16, 17, whatever. Okay, anything less than 20. Less than 20. Okay, so that the wires themselves wouldn't overheat or melt. Hmm. Okay, describe what is observed in total internal reflection. Okay, this is a nice question. What is observed in total internal reflection? Does any of the light refract? Does any of the light escape the medium? No. All of the light remains inside the medium. All of the light remains inside the medium. So no refraction. You can say no refraction. All of the yeah, all of the light is reflected back inside the medium. Inside the medium. Okay, all of the light is reflected back inside the medium. State two conditions required for the light to be totally internally reflected. Nice question. Two conditions. First of all, you need to say that the light is moving from which medium to which medium? From the less dense to the more dense, or from the more dense to the less dense? Definitely, the light has to be moving from the more dense to the less dense. Light must be traveling from the more dense medium, from the water, from the glass, or whatever, okay, more dense medium to the less dense medium. And the second condition, which is the more obvious condition, total internal reflection happens when the angle of incidence is greater than the critical angle. When the angle of incidence, okay, is greater than the critical angle. Okay, describe and explain the action of optical fibers. Communication in communication technology, you may draw a diagram in your answer. Communication technology, our everyday use. We use internet. Actually, our internet is provided using what? Using optical fibers. What happens that we have this optical fiber? Okay, what happens in the optical fiber? Light travels into the optical fiber. Okay, and then it totally internally reflects until it reaches the other side, totally internally reflects until it exits from the other side, carrying information. Okay, yeah, light travels. Hmm. Could be light, could be part of the infrared. Some of the infrared radiation can be used in optical fibers. Okay, light travels inside the optical fiber. Okay, totally internally reflects, totally internally reflects inside the fiber, carrying information, carrying information to the other side. Information to the other side. It's all about total internal reflection. It's all about total internal reflection. Carrying information, carrying data, whatever. Hmm. A radiation detector, a radiation detector is placed on the bench in a laboratory. It detects the background count rate of 40 counts per minute. Background count rate of 40 counts per minute. What is meant by the background radiation? Background radiation. It's a random background radiation. Huh. What is the random background radiation? It's a radiation that's there. It's always there. Due to what? It's always there. Due to whatever whatever surrounds you, anything in the environment, even you produce some background radiation. Okay, so it's radiation due to the environment. Okay, radiation due to the environment. Okay, radiation. Okay, let me write it down in another way. Radiation that's always there, that's always there due to the environment, or due to be more specific in things inside this environment, such as due to rocks and buildings. Okay, and the sun, the cosmic microwave background radiation in unit 6. Okay, CMBR. Okay, the sun have so many sources of background radiation. Radon gas, which is quite radioactive. Okay, radon gases. Yeah. Hmm. A sample containing atoms of the radioactive isotope polonium-208 is removed from a lead container, brought close to the detector. The average count rate increases to 890 counts per minute. When two sheets of paper are inserted between the sample and the detector, the average count rate returns to 40 counts per minute. After you only add two sheets of paper, okay, the radiation falls to 40 counts per minute. Deduce the type of radiation emitted by polonium and explain your answer. What is the only type of radiation that is produced by polonium for this case, for this question? Alpha. Alpha only. Why is it only alpha? Only alpha particles. Why are only alpha particles emitted? Why are only alpha particles emitted? Because alpha particles are stopped by the sheet of paper. They cannot pass through the sheet of paper. Okay, alpha is stopped by the sheet of paper. Okay, it cannot penetrate this sheet of paper. Beta and gamma, they can penetrate this sheet of paper, but the alpha particles cannot penetrate them. Hmm. Write down the nuclear notation for the decay of polonium. Okay, polonium produces lead, Pb. It produces what? Lead, Pb. Can I write down the nuclide equation? Yes, definitely I can write down the nuclide equation. Polonium 208, 84. It produces what? It produces alpha, which is 4 and 2, plus lead Pb. Lead Pb. Yeah. Pb, which would have a mass number of 204 and an atomic number of 82. Atomic number of 82. Okay? Okay.